Hi, this next project is on building uninterruptible power supplies using supercapacitors. So I've got a couple of these here. This here is one that runs off of a 12-volt supply. It's got a total of 5 supercapacitors, and there's a little voltage regulator that produces 5 volts, which runs a Pi 0W. Now there's kind of a bit more. This is actually piggybacked on top of another board, which is a Raspberry Pi based SCSI adapter. And maybe I'll talk about that a bit later in the video. I'll probably do a separate video on that, but basically this one here is my 12 volt to 5 volt uninterruptible power supply. And then I also designed another one here. This one is just straight 5 volts. So we've got 5 volt comes in. It charges just 2 supercapacitors, but they're really big ones. They're like 50 farads each, I think. And then there is a buck boost converter that takes the voltage from the 2 supercapacitors and uses it to run the Raspberry Pi. So why would you want a uninterruptible power supply for your Raspberry Pi? Well, I can think of 2 different reasons. One of them is, so with the typical UPS, if you have a hiccup in your power, you lose power for a couple seconds, it can keep the device operational so it won't have to shut down. So typically with computers we use those if there's a power outage due to a storm in the area that causes the power to be interrupted. You get uninterrupted operation of your device, even without the power. So it turns out that these supercapacitors, they're really not going to last you all that long in a power outage. You're talking just tens of seconds perhaps. So if you really wanted to be able to keep your Pi running during a power outage for any respectable amount of time, you'd probably want a solution that used a lithium battery instead. So that brings us to kind of the second purpose of one of these. If it's not really to keep the device operational for the duration of a power outage, what it could be done to do is to allow the device to be shut down safely. So a Pi is a general purpose Linux computer. You have open files, you have a file system on your SD card. If you just rip out the power cord while it's running, you could corrupt your SD card and you could damage your file system, and you could just lose the data that's in memory at the time. So what we can do with a supercapacitor is it can hold just enough juice to power this Pi for, let's say, 30 seconds to a minute or so. And that's enough to close open files, to shut down running processes, to flush the disk, and to put the device into shutdown so that our SD card will not get corrupted. Here is the schematic for the 12 volt UPS board. Now, I used as inspiration for this, I used David Gueswin's MFM emulator project, and the MFM emulator project is where I got the idea for how the supercaps are charged and for the DC-DC converter. So there are 5 stages to the supercap charger over here. So 1, 2, 3, 4, 5 capacitors. Each capacitor is 10 farads at 2.7 volts. And connected to each capacitor is a 2.5 volt shunt regulator right here. There's shunt regulator there, and there. And those shunt regulators will ensure that at most 2.5 volts will be across this capacitor. And that will keep a capacitor from getting overcharged, and it will also balance out the charge across all of them. Now there's some resistors also here in series. Those resistors will cause these capacitors to eventually discharge on their own. There's an LED here as well as a dropping resistor that will show when there is charge in the capacitor bank. And then out of the capacitor bank we have a diode here. So pretty much this whole section here is the capacitor bank. And then one-way current comes out via this diode to run into the DC-DC converter. Now for charging the capacitors as well as for discharging the capacitors, we have a 10 ohm 3 watt resistor. That limits how much current can go in to charge this bank at any one time. The resistor actually hooks up to a jumper block where you can either choose to charge the bank, or if you want to work on it, you can discharge the bank in a hurry. So over here we have our DC-DC converter. Now I've actually got 2 footprints. One of these is for the module that David used in his MFM emulator. That is a commercial module you can get from DigiKey. It takes a programming resistor that sets the value of the voltage coming out. It's set for 5 volt. The other footprint I've got is a 7805 footprint. Not because you'd actually want to use a 7805, that'd be really wasteful, but because you can buy little easy SBC DC to DC switching supplies that have a 7805 footprint. So you can actually get those in 3 amp version, so I have the option I can use one of those there. Then we've got some filter capacitors on the inside, filter capacitors on the outside. There's some fuses here just to, in case something goes wrong, there could be a lot of energy in these caps. You can want to limit what happens there. Then we have an AT Tiny 85. And the AT Tiny 85, it serves as the brains of the whole thing here. So it is monitoring the voltage coming from the input as well as the voltage in that capacitor bank. And it is reporting that voltage to the Raspberry Pi. So there is a library that you can use on the Tiny 85 that will look like an I2C target device. So just like any other I2C device, this will look like it has registers that you can read and write from the Pi. So what it does is it constantly samples the voltage on the bank as well as the voltage coming in and reports those to the Pi. So the Pi can query this chip and it can determine whether we are in a power outage situation as well as it can determine the health of the batteries. Now, when sampling those voltages, there are a couple of resistor network dividers there and there because 12 volts is too much for the ADC, so we divide it down by a factor of, I don't know, maybe around 5 or 6. So we wanted 2.56 volts to be full scale around 12, so it's kind of scaled so that if there's 12 volts here, it reads as 2.56 volts going into the A to D in the Raspberry Pi. Now the next thing is that there is a circuit here that is a MOSFET switch. And the MOSFET switch, what it does is it allows the AT Tiny 85 to turn the power on and off going to our Raspberry Pi. So it is a high side switch, so the power comes in at the top, and then if you put, I believe if you put a low voltage here on the gate for that switch, then the power will flow on through to the power output. So under microcontroller control, we can switch the load on and off. Now that power out comes out to various footprints. It goes out to a USB jack. It goes out to a couple headers here that have I2C on them, as well as power and ground. It comes out to some 5-volt pads on some floppy and hard drive connectors. It's just basically, I designed this board so I could use it in a variety of scenarios. What else is on here? Well, there's an ICSP header here so that we can program the thing without having to remove the chip. There are some resistors here that make it look like an Apple charger. So you hook an iPhone up, it will sense the voltage on those USB pins and it will think this is an Apple charger that it can get, I don't know, 2 amps out of or something. I forget what exactly it emulates. You can pick different resistors and they'll look like different kinds of chargers. That's pretty much it. It's pretty simple. So when the power is connected, the power flows via this path, charges the capacitors, also flows via this path, powers up the DC-DC converter, out through the MOSFET switch and into the Raspberry Pi. When the power is disconnected, the power flows out of the capacitor bank this way into the DC-DC converter, still into the MOSFET switch, and still out into the Raspberry Pi. Now, as far as the software goes, there are 2 parts to this. So there is the Tiny 85 on the UPS. And over here, we have the Pi with a Python daemon that I wrote. So it starts out, everything here is happy. And the Raspberry Pi will say, is power good? And let's say the UPS says, no, power lost. This is going over the I2C bus. So the Raspberry Pi will say, is the power good? The UPS will say, no, the power was lost. So that, now we're upset. We say the power is lost. Let's do a shutdown. And then we will unmount everything. And then we will go read only. And then eventually we'll be kind of cautiously optimistic again down here that we've safely secured our file system and that we can be powered down. So the Raspberry Pi will say back over I2C, it will say shut down to the UPS, and then the UPS will cut the power to the Raspberry Pi. So relatively simple protocol going back and forth. So I've made the protocol look pretty simple, but there are some intricacies involved. For example, the AT-Tiny5 has a startup sequence where it waits for the batteries to be charged. It won't power on the Pi until it has some minimum amount of power. Also, after we have shut down, there's the Tiny85 will go into a mode where it's waiting for someone to depower the device and then repower it so that it knows that it should bring the Raspberry Pi back online. Various scenarios like that. It's kind of a little state machine runs inside of the Tiny85 where it's able to keep track of what all is going on. Okay, here is my 12-volt UPS prototype. So you can see it's got 5 supercapacitors. Each one of those is 10 farads at 2.7 volts maximum. We've got the 1, 2, 3, 4, 5 shunt regulators to go with them. We've got the DC-DC converter here that will convert from anywhere around 7 volts on down to 5 volts. Here are a couple diodes, so the current only flows one way. Here's the dropping resistor for charging the capacitors. Here we have the AT-Tiny85, various resistors for the voltage dividers, in-circuit programming port. Here's an LED that shows if the capacitors are charged. Here's an LED that shows if the power is on. Now I put several different jack footprints on this, so I've got actually a 4-pin floppy connector where the 12 volt can come in here, or I've got a barrel jack. I've got a USB connector where the 5 volt can come out. I've got various floppy or hard drive connectors where the 5 volt can come out down there, so I can just put this in various use cases. And then on the bottom I've got a header that allows me to easily piggyback it onto my RA SCSI prototype. Okay, let's give this a shot. So over here I have a multimeter hooked up to the supercapacitors. I'm not sure why it's slowly ticking up. Maybe I've got some leakage into the circuit from this HDMI monitor or something. But ignore the fact that it is slowly ticking up. It is showing the current voltage across the bank of supercapacitors. Here we have an HDMI monitor that is connected to the Pi 0W. Here's the Pi 0W, and here is the UPS. So here's my power. I'm going to plug it in, and when I plug this in we will see the capacitors begin to charge really pretty quickly. There we go. So capacitors are charging. I have it set so once it gets to about 8 to 8.5 volts it's going to turn on the Pi. We wait until it's got some charge in the caps because we do want some expectation that we should be able to power the Pi if we have an immediate disconnect. So there it is, powered it up. Here we can see the Raspberry Pi 0W booting up. So okay, we've got about almost 11.5 volts in the supercapacitors. It's still slowly ticking up. I'm going to pull the power now and we'll see it do a shutdown sequence. Now when I pull this, we will see that the Raspberry Pi will detect that the power has been lost. And when it detects the power has been lost, it will initiate a shutdown sequence, basically by running SBIN shutdown. And then once that sequence completes, then it will notify the UPS that we're ready to power off, and the UPS will shut off the output. So here I'm going to pull it. Here we can see that the voltage is dropping. There it has detected the loss of power. It is shutting down. And there, it safely shut down, unmounted everything, and it powered itself off. Now we've still got quite a bit of juice left in those supercaps, so we could have continued to discharge for quite a long while if we'd had a longer shutdown sequence. I can get at least 30 seconds, maybe a minute out of this. I haven't really totally benchmarked it yet. But if we restore power, we will see that immediately it already has enough juice in the caps that it says it can turn on. It's booting up. So here is the schematic for the 5-volt version of the circuit. So I kind of kept it mostly the same as the 12-volt. We've still over here we still have the supercapacitor circuit. We still have a dropping resistor. I've changed the rating on the dropping resistors now. Instead of 10 ohms, we'll go down to about 3.3 ohms. Instead of 5 capacitors for 12 volt, we now have 2 capacitors that we will use for 5 volts. So we'll try to put about 2.5 volts in each one of them. We still have the shunt regulators that ensure that no capacitor gets overcharged. We still have the jumper that lets you select between charging and discharging. We still have the voltage dividers over here to drop the 5 volts down to about 2.56 volts. We still have the tiny 85. But one thing I did change is I did change the DC-DC converter. So now we're no longer in a situation where we have a large amount of voltage over here like we did with the other circuit where we had about 12 volts and we wanted to step it down to 5. Now we're in a situation where we have at most 5 volts here, probably less than 5, because as this discharges it's gonna go on down, and we're going to want to step that voltage up to 5. So this, I went with a Pololu buck burst converter. Now I only went with a 1.5 amp converter. I kind of wasn't thinking, because if I was thinking about Raspberry Pi 4 I would have picked a bigger converter. But this converter, as this voltage declines, it will maintain a constant 5 volt out there until it hits about 3 volts, then it will go into an automatic shutdown. Now one problem with this converter is it becomes pretty inefficient as our power is dropping, particularly on something like a Pi 4, which is a power hungry, for a Raspberry Pi is pretty power hungry. Once you get down to about 3.3 volts coming into this converter, it will start to have trouble supplying that Pi, and I think that Pi goes into under voltage and shuts off. So what I eventually will do, I think I'm going to respin this board, and I'm going to replace this 1.5 amp buck boost with a simple, I think Pololu has an 8 amp boost converter. That will be more than enough capability to supply our Raspberry Pi, and it will not have that problem where it becomes inefficient and then has to shut down. Over here we have a standard 40-pin header for a Pi. We've still got an ICSP for the Tiny 85. We've still got here a USB out, just in case I don't want to use this as a hat and I just wanted to use it as a general purpose 5 volt power supply. I've got the USB output there. We've still got a header here for the I2C. We've still got a barrel jack that you can use to power it. Very similar to the 12 volt schematic I showed earlier, but with 2 stages instead of 5 and with a different DC-DC converter. Now you've noticed, if you were looking at the other schematic, I had a MOSFET switch that would turn power on and off to the load on that 12 volt schematic. I eliminated that MOSFET switch and I went with simply switching the DC-DC converter itself on and off. So there is an enable line on the DC-DC converter. So what the AT Tiny can do is it can simply turn that converter on and off. That turns the load on and off. Now you might ask, where is the AT Tiny 85 getting its power if it's not running off of the boost converter? Well, since this is at most 5 volts here, the AT Tiny 85 can run directly off of these capacitors in a no power situation. So Tiny 85, the standard version of it, is good down to like 2.7 volts. I think the low voltage version of it may be good to even like 1.8 volts or so. You can get a pretty low voltage version of the Tiny 85, so you can simply run it off of the supercapacitors directly if you need to. and that allowed us to get rid of that MOSFET switch. So here's the 5-volt board. So first of all, this conglomeration here is 3 resistors in parallel. I really wanted to put like a 3.3 ohm or even a 2.2 ohm resistor in, but all I had was 10 ohms, so I hooked several of them together. I'm going to order some 2.2 ohms probably and replace those. You've got the 2 supercaps. These are each 50 farads at 2.7 volts. You've got the AT Tiny. You've got the buck boost converter. This is the Pololu buck boost converter. An LED here to show it's charged, an LED to show it's on. Barrel jack for power coming in. Here's the 2 regulators that go with the supercaps, the diodes to give us the one-way power flow. And then we've got a header down here so that we can plug it into a Raspberry Pi as a hat. Okay, here we have the Raspberry Pi 4 hooked up with my 5-volt prototype. On this side we have the meter hooked up to the supercaps again, measuring the voltage on the supercaps. And we have the HDMI monitor. Now I'll power this up. And again, it's going to charge the supercaps. It's not going to turn on until we get a significant amount of voltage on those caps. Set the threshold maybe somewhere around 4 volts if I remember right. So we'll wait for it to build up. Okay, there it turned on, so I had the threshold set to about 4 volts, so the Raspberry Pi is now booting up. Okay, let's pull the power now and see what happens. Okay, so the Raspberry Pi has noticed that the power was removed. We are now switched over running off of supercaps. The supercaps are draining, and the Pi is starting to shut down. But we just hit an undervolt alert on the Pi, so the DC-DC converter is starting to have some issues. Down to about 3.8 volts, 0.7, and boom, we actually overloaded. So what happened is we actually ran out of juice coming out of the DC-DC converter. I think that converter gets less efficient as the power goes down, and we just didn't have enough to continue operating the Pi. So obviously this isn't quite long enough. We got maybe about 10 seconds out of it before it shut down. So I think there's about 3 problems that I need to resolve to get this working. So first, you'll notice we only got up to about 4.4 volts on the capacitors. Part of that is the voltage drop in the cable. Part of it is the voltage drop across this resistor that I was using to charge the capacitors. So that cost us like 0.6 volts that we could have put in our capacitors, but we weren't able to put into there. So we lost quite a bit by not being able to charge these up to full. I'm going to have to see if try using a different cable. I can try putting in a different resistor. Maybe we can get a little more charge in those supercaps. The second problem we had was this regulator that gets less and less efficient as its input voltage goes down. Once it gets down to about 3.5 volts, this thing is down to, I think, 80% efficient, maybe 75% efficient. Its maximum current also goes down, and I think it just didn't have enough oomph to keep running the Raspberry Pi. So I can try replacing this regulator with a different one that will be able to put out more current and will be more efficient throughout the voltage range. The other thing we can look at doing is it just kind of took this Pi a long time to shut down. It took it like 10 seconds. Maybe if I optimize the shutdown procedure, I could get it to shut down a little bit quicker. But all things considered, a little bit disappointing. I had hoped this solution would just work on a Raspberry Pi 4, but it's going to take, I think it's going to take a little bit more thinking, and I'm going to respin this board and see if we can make it work. Okay, just because I can, I'm also going to try this same experiment out with a 5-volt board and a 0W. So the 0W, see it's sandwiched down there beneath, where the Raspberry Pi 4 was a moment ago. Again, we've got this hooked up to the supercaps. Let's plug this in and let it start charging. There you can see we're starting to build power in the supercaps. There, we hit the threshold to turn on, so it's starting to boot up. Our 0W is booting. Okay, so one thing you'll notice is that we've got a little bit more juice in the supercaps. That's because the 0W is taking a lot less power than the 4 was, and there's actually less voltage drop in this supply cable. So it's more voltage is getting to the board, so it's charging the capacitors up a little bit higher. So let's try pulling the plug and see what happens. There it has noticed that the power has been discontinued. It is shutting down. And it has shut itself off and turned itself off. Well, that was very quick. So for whatever reason, the 0W was able to shut down very quick in just a couple of seconds, whereas the Pi 4 seems to take a very long time to shut down. So again, I think if I was to take the Pi 4 and optimize its shutdown sequence, figure out why it's taking so long, maybe it would be a viable shutdown for the Pi 4. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.